Alrighty folks, we are going to be looking today at factoring special trinomials. These are not special like your weird Uncle Harold is special, just special in that they're unique in some way and require a bit of special attention, extra attention. For example, factoring perfect square trinomials, we're going to take a second to kind of look at what those look like. Something like x plus 4 times x plus 4, which is the same as saying x plus 4 squared, which is why they're called perfect square trinomials. Now, if you actually multiply this out, you can do it pretty easily. Here it is here. Okay, and I mean, this kind of trinomial, you can factor the old-fashioned way, in other words, looking for the magic numbers, but recognizing a perfect square trinomial just takes a lot of the work out of it. And so we're going to look for some patterns. Let's look at some other ones here that we have here. I'll write a bunch down for you. Okay, there's 4 different perfect square trinomials on the right there, and their products, their factored products on the left. They're all perfect squares. Just take a moment just to kind of look to see if you can see a pattern. Let's just look at the first two here at the beginning and see if you can see a pattern between, or a connection between, the last term and that middle coefficient. Okay, well, you should recognize that the square root of 16 is 4, and then 2 times 4 is 8, and 8 is the middle coefficient. Well, let's see if that works with the second one. In other words, I'm going to take 2 times the square root of the last term. Well, the square root of 49 is 7. 2 times 7 is 14, and that is indeed the same as the middle coefficient there. And that will work for any one that we do that is a perfect square. So if I'm looking at a trinomial like this one, x squared plus something x plus 81, in order for this to be factorable as this, x plus 9 squared, that middle term then has to be 18x, okay? Because that is 2 times the square root of 81, 2 times the square root of that last term. Okay, and that's how we get to that middle term. And so then, again, knowing all those perfect squares becomes really helpful, because something like this one here, you should be able to look at it and go, okay, well, I know that the square root of 121 is 11. 11 times 2 is 22. Therefore, this is factorable as a perfect square. And all you do is take the square root of the first term, which is x, and the square root of the second term, which is 11. Sorry, the square root of the third term, the constant term, 11. And that's it. It's just x plus 11 all squared, and you're done. So recognizing it saves you from having to look for the magic numbers, listing out all the factors of 121 and going through and finding the ones that add up to be 22, whatever the case may be. So this is going to make things a little bit easier for you. Let's look at the second set that I showed you before there. Okay, so looking at the bottom ones now. And the same thing doesn't seem to exist. The square root of 9 is 3. 3 times 2 is 6. So it doesn't work there. The square root of 36 is 6 times 2 is 12, not 60, looking at the bottom one there. So just like in the when we started learning how to factor these, we had to change our algorithm, if you will, to include this first term. Okay, and we're going to do the same thing here. So let's look at the square root of both of those. The square root of 4 is 2. The square root of 9 is 3. That's equal to 6. 2 times 3 times 2 is equal to 12, which is what the middle term is there. Let's do the same thing for the bottom one. The square root of 25 is 5. The square root of 36 is 6, which is 30. And again, times 2 is 60. So that same pattern exists. It's the square root of the first term times the square root of the second term times 2. And again, because this was just a 1 here before, we didn't have to really worry about it, but we were doing the same thing. Okay, so the square root of 1 is just 1, so we're always just multiplying by 1. But that's the pattern that we're looking for. So this polynomial will be factorable as a perfect square if, so we're looking at then, if rather, the square root of c times the square root of a, and all times 2 adds up, or sorry, multiplies together to give you b. Okay, so that's the pattern we're looking for. The square root of a times the square root of c, all times 2. If it equals b, then all you have to do to factor it is just take the square root of a and put an x after it, or whatever that first term is, the square root of the first term, plus the square root of the second term, or the constant term, and then just square it. That just sounds really terrible when I say it, but when I show it to you, you'll see what I mean. Let's look at some examples here. Okay, so imagine your delight if you were to see this kind of problem in a factoring question. You would probably crap your pants. And I get it, because 144 has a bajillion factors. If you're doing the shortcut method, you'll be doing it forever. So we're trying to, and there's no common factor there either. Like 3 doesn't go into anything. Sorry, that's not true. 3 goes into all of those. So I could factor out a 3 here first. Actually, I can factor out a 9. Never mind a 3. Let's take out a 9 instead. Huh, well, you know what? We just made this problem a whole lot easier, which is a good lesson for us all to always look for the greatest common factor. But, again, that pattern we're looking for, though, is the square root of the first term times the square root of the third term times 2 should equal the middle term. And it does, because the square root of 16 is 4, 4 times 1 is 4, times 2 is 8. So this is factorable as a perfect square, so then all I have to do from here, without having to search for any of my magic numbers, is simply just go the square root of 16x squared is 4x, the square root of 1 is 1, and I'm done. Just like that. Just by being able to recognize a perfect square. Let's look at one maybe that doesn't have a giant GCF that we can pull out and make it a little bit easier. Okay, here's one. And again, this is where you're going to really wish you knew all of the perfect squares, because the first and last term are in fact perfect squares. I know that the square root of 49 is 7, and the square root of 169 is 13. And by the way, is 91, and if I multiply that by 2, look at that, I get 182. So being able to, again, to recognize what those relationships are eliminates you having to go through and do all those ridiculous steps. Can you imagine for this right here, trying to find two magic numbers? This is what you would have to do if you don't do it this way. Okay, if you don't know the shortcut here, you would have to look for two numbers that multiply to give you 8,281 and added to give 182. So just imagine trying to find all the factors of 8,281, listing them all down. It would take forever. Okay, but recognizing that 49 and 169 are perfect squares, I can simply look for that relationship, which we've already proven is there. So then all I have to do to factor this is, okay, the square root of 49x squared is going to be 7x. The square root of 169 is 13. Done. Just like that. Nothing else is necessary. No magic numbers are needed because I was able to recognize that this is a perfect square trinomial. So pretty important stuff. Alrighty. Alrighty, so what I would like you to do then is, for these four trinomials here, some of them are perfect squares and others of them are not. So if you wouldn't mind just writing those down, and you can factor all of those. If you can recognize them first, look for the ones that are perfect squares. It'll make it a lot easier to factor them. Once you have that, you can get those done. The ones that are not perfect squares, you have to factor the old-fashioned way. So it'll save you some time if you can see it. Hopefully you can. We'll discuss this tomorrow, as well as talk about something called a difference of squares, all that and more tomorrow's class. See you then.